everyone, this is the second part of the 31st video for the course Mathematical Methods for Economics, and in this part we are going to talk about series. In the first part we looked at sequences of numbers, and the question now is, what if we want to sum up, because a sequence of number is a listing of numbers. So what if we want to now sum up the numbers in the sequence, whether it's a finite sequence or an infinite sequence of numbers. And what we want to know is, okay, fine, you can add two numbers, you may be able to manage even the addition for a few numbers, maybe several, but if you have several numbers, and what if you have to add infinitely many numbers together? So if this is the kind of question that we have, where we have to add many numbers, infinitely many numbers together, then it is precisely this question that we address in this part of the video, where we bring in the idea of a series, which is nothing but the sum of the terms in a sequence. We will specifically be talking about a geometric series, and we will cover both finite and infinite geometric series. Let us first look at a finite geometric series. Let us suppose you have a sequence of n numbers, which is given by, the sequence is given by a, comma a times k, ak squared, and so on, where the general term is ak to the power n minus 1. Here in this sequence, a is the first term, and there is one thing unique about this sequence, which is that every number starting from the second is generated by multiplying the previous number with the constant k. So, k is a constant, and if you notice here, if I were to divide any number after the first one, any number by the previous number, then that ratio is going to be a constant, which is k. So, if I take ak divided by a, that's going to be a k, or ak squared divided by ak, that's also going to be a k. So, basically every term is generated by multiplying the previous term by the constant k, and that is why k is known as the common ratio, because if you take the ratio of any term with the previous term, the ratio is a constant k. So, this k is known as a common ratio or the quotient. Now, with this sequence, let us define the sum S sub n, which is equal to a plus a times k plus a times k squared, and so on till a times k to the power n minus 2 plus a times k to the power n minus 1. It is this sum that we call a finite geometric series. There is a finite number of terms, and there is a certain pattern to this series, where the sum is generated from this particular sequence, where you have a common ratio k, right? You have a multiplicative constant k. Right. Let us look at some examples of finite geometric series, and what I would like you to do in each example is to specify what the first term is, what the common ratio is, and how many terms we have. So, this is a simple question, and let us look at each series one by one. So, in the first series, you can clearly see that the first term is 2, right? The common ratio is 3, because 6 by 2 is 3, or 54 by 18 is 3. So, in this way, you can check for each pair of numbers where you get the quotient as 3. And clearly here, the number of terms in this series is 5. Then look at the second series. In the second series, we have the first term as 3. The common ratio is 0.1. So, you can see here, if I multiply 3 with 0.1, I get the next term, which is 0.3. I multiply 0.3 with 0.1, I get the next term, which is 0.03. So, the common ratio is 0.1, and as you can see here in this series, we have 7 terms. In the next series, we have 10 terms, the first element being 1, and then the common ratio here is root 3. So, if I take the ratio of any two consecutive numbers, so root 3 ratio with the previous number, that's root 3, 3 by root 3 is also root 3, and so on and so forth, right. So, this is these are the three components that you have to look out for. Now, what we are interested in is a summation formula for a finite geometric series. What exactly does this finite geometric series sum up to? What exactly do these terms sum up to? Now, our sum is denoted by S sub n, which is a plus a times k plus ak squared and so on till ak to the power n minus 1. Now, to arrive at a summation formula, we are going to use this trick, which actually is very helpful, because what I will do is I can multiply both sides of this equation 1 by the constant k. Now, once I do that, I get k times S sub n on the left hand side, and on the right hand side I get a times k. If I multiply a with k, then I get ak squared, then I get ak cubed and so on till the last term, which is ak to the power n. Okay, when I multiply ak to the power n minus 1 with k, I get ak to the power n. When I multiply ak to the power n minus 2 with k, I get ak to the power n minus 1 and so on. So, this is how I generate 2. Now, what I can do is, if I subtract 2 from 1, the left hand side would become Sn minus k times Sn, right. And now if you subtract the terms on the right hand side of 2 from the terms on the right hand side of 1, you can see that all the terms will vanish. Ak will cancel out this ak squared will cancel out this ak squared, and all the terms will go away except for a and ak to the power n with a negative sign in front. You can do the subtraction on your own and check this result for yourself. Now, we are in a very convenient position to arrive at the summation formula for a finite geometric series, which is S sub n equal to a minus ak to the power n divided by 1 minus k. So, this is written as a times 1 minus k to the power n divided by 1 minus k. Now, if you notice here, because division by 0 is not defined, we will have to restrict ourselves to taking a k which is not equal to 1, right. So, our summation formula is a times 1 minus k to the power n divided by 1 minus k. Mark this formula. This is a formula which we will be using again and again for the examples that we do for finite geometric series. Now, here you might also ask what will happen if k is equal to 1, and clearly see you can't use this formula. But let me just back up, let me just back up. Yeah. So, another way of writing this formula is also a times, because if I take minus common, so I can also write this summation formula as a times k to the power n minus 1 divided by k minus 1. Okay. But again, k can't be 1. The question now that you might be thinking is about is what if k is equal to 1. Now, let us just think, let us just go back to first principles, the basics here. Now, see, if k is equal to 1, what does your series become? It will be nothing but a plus a plus a plus a and so on till n times, because you have n terms here. So, when the value of k is equal to 1, you are simply adding up a n times, and the result is simply going to be n times a, right. It is a very simple result. You do not need to use this formula will not even work if k is equal to 1. So, this formula we will use when k is not equal to 1. Okay. Let us take an example here to understand how we can find the sum of the finite geometric series. So, here you have this series 1 by 2 plus 1 by 4 plus 1 by 8 and so on till 1 by 2 to the power n. Now, what I would suggest is, because in the summation formula, what are the variables that we have to calculate, what are the ingredients that we need? One is a, because our formula is a times 1 minus k to the power n divided by 1 minus k. So, whenever you are writing a finite geometric series and you want to find out the sum, identify your a, the first term, identify the common ratio, and you will be able to get at your result. So, here the first term is half, right. K, the common ratio is half again, because if I take the ratio, let us say 1/4 divided by 1/2, that is nothing but half, right, or 1/8 divided by 1/4, that is also half. So, k here the common ratio is half, and you can see here that the sum would be given as, and the finite geometric series, because it is a finite number of terms, will always have a finite sum. So, the first term, which is half, times 1 minus k to the power n, okay, the whole thing divided by half. The half gets cancelled, in both the numerator and the denominator, and you are left with 1 minus 1 by 2 to the power n. This is the sum for this particular geometric series. Let us look at another geometric series, and here you have the example that I had given in one of the earlier slides, 3 plus 0.3 plus 0.03 plus 0.003 and so on till 0.000003. There are 5 zeros, then 3. And actually this addition is very simple. It's very obvious that you're going to be getting this result 3.333333. But let's just use the formula that we have derived for a finite geometric series to see if we actually get this result, right? So, here in this example, our first term, by the way, I can also, the question could also be written like this, that you have the series 3 plus 0.3 plus 0.03. Instead of writing all the terms, I can go up to the general term, that is 3 times 0.1 to the power n minus 1, and then I could, the question could ask you, do the summation for n equal to 7, right? And that is exactly what we have here. Okay. So, A is equal to 3, K, the common ratio is 0.1. So, the sum becomes the first term, which is 3 times 1 minus K to the power 7, because we have 7 terms, right. So, that is going to be 0.1 to the power 7, the whole thing divided by 1 minus K, which is nothing but 0.9. Now, once you do the calculations, you can use a calculator here. So, you are going to get, first of all, 3 and 0.9, this you can simplify, and that will give you a 0.3 in the denominator. So, in the numerator, if I simplify further, I am going to get 1 minus this expression, all these zeros. You can count the number of zeros on your own, the whole thing divided by 0.3, and that then gives me 0.9999999 divided by 0.3, and that is nothing but 3.333333. So, this is giving exactly the sum that you would get even if you were to just do this mentally, but this was just a good way to practice the particular problem. Okay. Now, what I am going to do is, I am going to walk you through an example from the textbook. I have adapted it from the textbook, and there is another example which will also get you started for the kinds of lectures that are to come, where we are going to be covering concepts in financial economics. So, but before that, let me walk you through this example. And this also generates a geometric series, a finite geometric series. So, in this example, we are talking about this guy Manu, who has a startup, and this startup is expected to generate an income of rupees 100 lakhs this year, which we will take as year 1. And further, the income is expected to be on average 16% higher in each successive year over the next decade, which is till year 10. The question asks you, what is the expected income in the 10th year? Okay, and let us look at that, and also it asks you to calculate the total income that Manu would can expect to get over the whole period. Okay, so if you look at this question, this year Manu is making 100 lakhs, right? The income that is being generated is 100 lakhs. Now, because the income next year, which is year 2, is going to be 16% higher, that value is going to be equal to 100 times 1.16. So, you can use your compound interest principles here. So, 1.16, okay. In year 3, the income is expected to be 100 times 1.16 from year 2, and that will grow again further. It will be 16% higher. So, 1.16, there will be another factor. So, in year 3, the expected income is 100 times 1.16 to the power 2. So, if you notice the pattern of things here, if I talk about year 10, then in this way the income expected in year 10 is going to be 100 times 1.16 to the power 9. So, this will be the income in year 10, and the total income that Manu can expect to get during this whole period would be 100 plus 100 times 1.16 plus 100 times 1.16 the whole squared, and so on till 100 times 1.16 to the power 9. Okay. Now, as you can see here clearly, this is a geometric series because there is this common ratio here 1.16, okay. K is going to be 1.16. There are 10 terms here and the first term is 100. So, we are all set to calculate the total income, and that sum is going to be given by 100 times 1 minus k to the power 10. So, that is going to be 1 minus 1.16 to the power 10, the whole thing divided by 1 minus k, which is 1 minus 1.16. Okay. That then gives us 100 times 1 minus 1.16 to the power 10 is, if you calculate, this is what I got, 4.4114, the whole thing divided by minus 0.16. Okay. And this then gives you 100 times 3.4114 divided by 0.16, which is nothing but 2132 lakhs. Okay. This is the calculation for this particular example. The example that I am showing you now is a good start for getting into things like finance, compound interest, financial economics, and let us take a look at this example. So, basically you have this person Maya who wants to be able to save enough to buy a house at the end of 2030. So, today is it's 2025 this year, which we are taking as year 0. Okay. And Maya is basically able to save 10 lakhs from a job or business, whatever. And what she does is every year starting from 2025, she puts the 10 lakhs that she saves every year in a fixed deposit that matures in 2030, because ultimately she wants the money in 2030 to buy the house. So, she is going to every year put 10 lakhs in a fixed deposit, and let us suppose the interest rate for the fixed deposit is 7% per year, it does not change. So, Maya's financial plan is as follows: on September 1st, 2025, she will put 10 lakhs in a 5-year fixed deposit. Remember that interest rate is 7% throughout. Then September 1st, 2026, because now there are only 4 years left till 2030, she will put another 10 lakhs in a 4-year FD. Then 2027, she will put another 10 lakhs now for a 3-year FD, then 2028, 10 lakhs for a 2-year FD, 2029, 10 lakhs for a 1-year FD, and then 2030, she already will be saving 10 lakhs. So, that she will straight away use for the purchase of the house. Okay. So, in 2030, she will use all the matured FDs, all the 5 FDs, and the 10 lakhs from that year to buy the house. So, the question asks you how much money will she have on September 1st, 2030. Let us see what that calculation turns out to be. So, when she puts 10 lakhs in a 5-year FD in 2025 this year till 2030, so that's going to amount to 10 times 1.07 to the power 5. Okay. After 5 years, which is in 2030, then the 4-year FD will yield 10 times 1.07 to the power 4, the 3-year FD 10 times 1.07 to the power 3, and so on. And this year you have 10 lakhs. So, all this money is going to be generated in 2030 for Maya to be able to purchase her house, and let us see how much that amounts to. So, if I take the first term, that is 10 times 1.07 to the power 5, right. Now, here if you notice, the common ratio is 1 upon 1.07. Right. Actually, what you could do is you could also write this series as 10 plus 10 times 1.07 plus 10 times 1.07 squared. You can go in the reverse direction, it is an easier calculation, but I thought let us just do it the way it is given. So, here our 1 upon 1.07 is a common ratio. So, I get 1 minus k to the power 6, there are 6 terms. So, 1 by 1.07 to the power 6, the whole thing divided by 1 minus 1 divided by 1.07, and that then gives you again the first term, then 1.07 to the power 6 minus 1, the whole thing divided by 1.07 to the power 6 as the LCM for the numerator, and then you have 1.0, when I take the LCM in the denominator, I am going to generate 0.07, right, and that is going to be divided by 1.07 here. So, you can see all the 1.07s will get cancelled, right, because in the numerator I have 1.07 to the power 6 and also in the denominator, so that will cancel out, and I am left with 10 times 1.501, which is your 1.07 to the power 6 minus 1 divided by 0.07, and that then comes out to be 10 times 7.158, which is equal to 71.58 lakhs. So, Maya can expect to collect 71.58 lakhs for her to be able to buy her house or apartment or whatever property she wants to buy. So, I hope this made for an interesting example. It is a very real life kind of example. Okay. The next part is also very important, where we are going to be talking about infinite geometric series. We have so far been talking about finite geometric series, but what about infinite geometric series, where the terms continue indefinitely, and the question is, can we give some meaning to this infinite sum, which is a plus ak squared and so on till ak to the power n minus 1 and so on, right. Now, if we consider the sum of the first n terms in this expression 3, the sum of the first n terms would be given by a times 1 minus k to the power n divided by 1 minus k. Okay. Now, what we will do is we will move from the n terms to the infinite case, and let us see how, because we will be getting an expression in the limit to be able to get at the summation formula for the infinite geometric series. Now, the sum of the first n terms is this, as we all know. The question that we can ask now is, what happens to this expression a times 1 minus k to the power n divided by 1 minus k as n tends to infinity, because that is what an infinite geometric series is all about. Okay. And again, remember, k is not equal to 1. Now, there are, if you notice here, I am asking what happens as n tends to infinity. Now, the only term that has n here involves a k to the power n here in the summation formula. So, what the result we get here is that as long as k lies between minus 1 and 1, in that case k to the power n will tend to 0. So, that our sum is a finite sum which is tending to a upon 1 minus k as n approaches infinity. So, if we want to get a sense of what this infinite sum means, this case would work quite clearly. So, that if the common ratio, as long as the common ratio is between minus 1 and 1, or the absolute value of the common ratio is less than 1, k to the power n will tend to 0 as n tends to infinity, and we get a finite sum which is a divided by 1 minus k, and we will use this limit as the definition for the sum given here in the box above. Okay. But remember here that this sum, this finite sum, which also leads us to conclude that the geometric series will converge, will work, this result will work only when the common ratio is between minus 1 and 1. However, if k is more than 1 or k is less than or equal to minus 1, then you can check for yourself. If you, let us say, take k equal to 2 or minus 3, then in that case k to the power n will just explode and it is not going to tend to any limit. Okay. So, our result here is that as long as absolute value of k is less than 1, then the sum of the infinite geometric series is given by a upon 1 minus k. And this then also allows us to discuss convergence or divergence for an infinite geometric series, because as long as mod k is less than 1, we are going to have an infinite geometric series that converges to a finite sum. Okay. So, as long as mod k is less than 1, the infinite geometric series converges. A divergent series, in contrast, is one that does not have a finite sum. So, if k is more than or equal to, greater than or equal to 1 or less than or equal to 1, or in other words mod k is greater than or equal to 1, then the infinite geometric series diverges. And because we can't use the formula for k equal to 1, so let us see what will happen if k is equal to 1, then in that case the sum would be, as we have already discussed, would be n times a, and you can clearly see here for a positive a and for n tending to infinity, this n times a will tend to infinity, and if A is negative, the sum will tend to minus infinity. Let's also look at what happens when k is equal to minus 1, because these are these border points which we would like to interrogate. If k is equal to minus 1, then the sum is going to be nothing but A for n odd, right, because our series would become A minus A minus A, and if n is odd, then the sum would be A, whereas if n is even, then the sum is going to be 0. So, clearly in this case also there is no limit as n tends to infinity. So, please remember these results for convergence. If we want to test for convergence a geometric series, that convergence will happen as long as the common ratio is less than 1 in absolute terms, or k is between minus 1 and 1. Otherwise, the series diverges. Let's look at a few examples to test your understanding. So, we'll go step by step. In each example, I'll ask you, you're asked whether the following series is a geometric series. Then in the second step, you'll test for convergence, the series that are geometric series. So, in this case, you'll just check for the common ratio. And then in the third step, if the series does converge, you have been asked to find the sum of that geometric series that does converge. Okay. So, our first series here, in fact, this I also took in the finite geometric series. So, half plus 1/4 plus 1/8 and so on, and you can see here this is clearly a geometric series with k equal to half. The series converges because k equal to half is clearly less than 1. So, the series converges, and because you are asked to find the sum now, that is the sum is going to be a divided by 1 minus k. So, that is nothing but half divided by 1 minus half, which is 1. And if you go back to the example that I did with you for the finite geometric series here, our finite geometric series gave us a sum 1 minus 1 by 2 to the power n. So, from here also if you take n going to infinity, 1 by 2 to the power n will go to 0. So, you get the series converging to 1. Okay. And also you must remember that when I talk of a series converging, I am talking of the sum of the sum in the series converging to a finite sum, right, to a single value. Whereas, when I am talking of a sequence converging, it is the nth term which is converging to a single value. It's a nth general term. Okay. Again, look at this geometric series. Here you can see that the first term is 5 by 4. If I take the ratio, it's clearly a geometric series because you can check for the ratio. It's the same for every 2 successive numbers. So, that's going to be there's a minus sign in every alternate number. So, there will be a minus 5 by 2 to the power 3. So, minus 5 by 8 is a common ratio, and again in absolute terms this is less than 1. So, the series converges, and the sum of the series will be 5 by 4, which is a, divided by 1 plus 1 plus 5 by 8, well, that is 1 minus k, and that then gives us 10 by 13. Let us look at a few more examples. You have minus 2 plus 6 minus 18 plus 54 minus and so on. Again, this is a geometric series with the common ratio being 3. The series diverges in this case because the common ratio is more than 1, and because it diverges, we do not have to do the third part where we have to find the sum. So, clearly this series is diverging. So, we are not concerned with the third part. Okay, and this series that you have here in part D, this is clearly not a geometric series, so the rest of the question does not apply. Okay, this series is x squared plus x to the power 4 plus x to the power 6. Here the common ratio is x squared, so it's a geometric series. And as you can see, the series will converge as long as, see, because x squared is not going to be negative. So, as long as x squared is less than 1, the series is going to converge. Now, x squared less than 1 is the same thing as saying that x lies between minus 1 and 1, which is to say mod x is less than 1. So, for mod x less than 1, the series converges, and the sum is going to be a upon 1 minus k, which is x squared divided by 1 minus x squared. Okay. This is an application that I have taken from the textbook, which basically gives you a rough estimate of the total oil and gas reserves in the ABC continental shelf at the beginning of 2024, which was 12 billion tons. Production that year was approximately 50 million tons, which is 15 to 10 to the power 6. The total stock was 12 billion, which is 12 into 10 to the power 9. The question asks you how many more years can the reserves last if production is kept at the same level. So, if every year you are extracting 15 to 10 to the power 6, 15 to 10 to the power 6, and how long can you go on extracting oil. So, clearly the total stock is 12 into 10 to the power 9. If I divide that by 15 to 10 to the power 6, which is the extraction per year, then that is 240 years. So, you can go on till 240 years and extract, use the reserves. But clearly then you are going to be depleting your stock and finish it off. But there is an expert who claims that extraction may be continued indefinitely if production is reduced by 1% every year beginning in 2025. So, the question asks you, is this plan feasible? Can extraction be continued indefinitely like this? So, let us look at the pattern of things. In 2024, production was 15 to 10 to the power 6. In 2025, because production is reduced by 1%, so production becomes 15 to 10 to the power 6 times 0.99, then 15 to 10 to the power 6 times 0.99 squared. And if you look at this sum, this turns out to be 5 into 10 to the power 9, which is clearly less than the total stock of oil and gas reserves, which is 12 into 10 to the power 9. So, clearly with this kind of an extraction plan, you can go on with the extraction process indefinitely, and that is clearly a more environmentally friendly way to use a particular resource. So, with this we close the second part of the 31st video. We will also be looking at a lot of problems from geometric series, and we will also look at convergence and divergence with respect to a general series, but we will leave that now for the next video. So, until then, goodbye, thank you.